So basically, this is a special kind of process for the preparation of BEF2. Okay, and I told you that compound of NH4 positive with anion is ionic. Like NH4Cl is NH4 positive, and here it will be Cl minus, and there will be force of attraction between these two, that is ionic in nature. Is that clear?
Yes.
Okay, another preparation of BeCl2, basically BeCl2 is prepared, that was BeF2, prepared by the reaction of, write with me, by the reaction of their oxide, that means BeO, with carbon coke and Cl2 as well. It will give BeCl2. If we are going to add beryllium oxide to coke and Cl2 at 600 to 800 Kelvin, it will be converted into beryllium chloride and CO, that is carbon monoxide. That clear?
Yes.
Okay, just write it. Then we will take a reaction with liquid ammonia. We'll proceed with that.
Done.
Very good. Now, the reaction with liquid ammonia. How S block elements react with liquid ammonia. Just see. I'm going to write some points, write with me. The dilute solution of alkali metal and liquid ammonia produces ammoniated cation and ammoniated anion. Ammoniated cation and ammoniated anion. Sorry, it is ammoniated cation. Ammoniated cation and I already wrote it here, and ammoniated electron. This is liquid and this is ammoniated electron. Just write it and I will explain it right now.
Done.
Done. Now see, there is a metal and it is going to react with ammonia, and just suppose ammonia has some coefficient, that is X plus Y. So since metal has a tendency to lose electron, metals are electropositive in nature, so metal will lose one electron, so it will be M plus, right?
Yes.
And here see, ammonia basically we will take in two parts, NH3 whole X, and one of the electron will go to this, like this, NH3 whole Y. Now you can see this is balance. NH3, total NH3 here is X plus Y into NH3, and on the right hand side X NH3 Y NH3, that represents X plus Y NH3, right?
Yes.
One of the metal is here and one of the metal is here. Charge, you can see here on the left hand side there is no charge. On the right hand side there is also no charge. Why? Positive,
Plus and
negative,
minus.
it will cancel each other,
Yes.
right? So there is important discussion about it. The dilute solution of alkali metal and liquid ammonia, right with me, and liquid ammonia imparts blue color. Imparts blue color. Why does this impart blue color, or why does this impart color? Because of this free electron. Because of this free electron. So I'm going to write it. It is due to the presence of. It is due to the presence of ammoniated electron. It is due to the presence of ammoniated electrons. Since it has free electron, unpaired electron, that means it is paramagnetic. Paramagnetic, what is paramagnetic? If there is unpaired electron, that is called paramagnetic. So I'm going to write it is paramagnetic due to presence of ammoniated electron. Just write it.
Done.
Very good. Now write reaction with water. Reaction with water. So if I'm going to take a reaction with water as for alkali metals, and here for alkaline earth metals. If lithium, that is an alkali metal, react with, or just take a general. If I'm going to take 2M with a 2H2O, that will give MOH, that is metal hydroxide plus H2. And here if you are going to add M plus 2H2O, that will give MOH whole twice, because it has a valency 2 and OH has a valency 1 and H2. The lithium is very less reactive towards it. Lithium is less reactive. As the size increases down the group, reactivity increases. But sodium, potassium, rubidium, and cesium easily reactive, or readily reactive. We can say easily react. Okay, just wait a minute. We are going to do it part wise. Easily react. And about rubidium and cesium, reacts with explosion. Highly reactive, reacts with explosion. What about here? Alkaline earth metal. Beryllium do not react with water, since it has more covalent character. That's why do not react with water. Magnesium reacts with water, reacts with hot water. Also calcium, strontium, and barium reacts with cold water. Just write it.
Done.
Very good. Right. Solubility of ionic compound S block. Solubility of ionic compound of S block. For solubility, we will have two terms. It has two factors on which the solubility of ionic compound of S block depends. So I'm writing a point. It depends upon two factors. The first one is hydration enthalpy. Hydration enthalpy that we have discussed already. Hydration energy, or we can say hydration enthalpy. Both are same. Now see what is hydration enthalpy. You can see the amount of energy, released during the interaction of the ions in water is called hydration enthalpy. Have you studied about it?
Yes.
So just suppose S block element, I am taking sodium, since we just dip sodium into water, so it will be converted into ions. And you know that water is basically polar in nature, so it will have some delta negative charge. It will have some negative charge, and oxygen here also. It will have some negative charge, so there will be force of attraction between them, interaction between them. And whenever there is force of attraction, energy will release. That energy is called hydration energy or hydration enthalpy. Is that clear?
Yes.
Okay. The next factor is basically lattice enthalpy. Lattice enthalpy LP. And you know that what is lattice enthalpy or lattice energy? Amount of energy required to convert 1 mole of solid ionic compound into its constituent ions in gaseous state. That energy is called lattice energy, and we have already discussed about lattice energy. Lattice energy is directly proportional to magnitude of charge, inversely proportional to size of ions. Is that clear, Akifah?
Yes.
Very good. Are you done?
Yes.
Okay. So moving to the next part, which is very important, how we decide which one is more soluble and which one is less soluble. So always remember, if lattice enthalpy is greater than hydration enthalpy, solubility will be decreased. Solubility of ionic compound decreases. Solubility of ionic compound decreases. And if lattice enthalpy less than hydration enthalpy, that means hydration enthalpy greater than lattice enthalpy, that means solubility of ionic compound increases. Is that clear?
Yes. Done.
Done. Just remember two important points, that since we are talking about ionic compounds and ionic compounds, there will be ions, that means cations, as well as anions. There I'm going to write a list for larger anions. Larger anions, you can easily recognize it by like CO3 minus 2, HSO4 minus, SO4 minus 2, We can say HCO3 minus, NO3 minus, and I minus and Br minus. It's all we consider it's all as larger anions. When we talk about a smaller anions, a smaller anions will be like F minus, Cl minus, OH minus, O minus 2, N minus 3. These all are a smaller anion. Is that clear?
Yes.
So here comes a point about solubility. Generally, solubility of ionic compound decreases from top to bottom. From top to bottom. From top to bottom, generally ionic character solubility of ionic compound is decreases. Like if we are talking about DeCO3, MgCO3, and CaCO3, SrCO3, and BaCO3. So the solubility basically here decreases. Why it is so? Why the solubility of ionic compound decreases? Just see, we have a formula in class 12th in electrostatic. Hydration enthalpy is equal to 1 by r, that means the radius of cation plus uh, radius of anions, and there will be k q1 q2, k q1 q2, that doesn't matter, will be almost and lattice enthalpy that will be equal to 1 by r plus 1 by r minus. R plus that represents radius of cation, r minus that represents radius of anion. Is that clear, Akifah?
Yes.
Since these all are larger anion, these all are larger anion, isn't it?
Yes.
So if these are larger anion, that means r minus is so large, and if it is in denominator, the overall value will be smaller.
Yes.
Are you getting my point? The more the the value in denominator, if it is high, that means overall value of that value is equal to very small. Is that clear? If I'm talking about 10 raised to the power minus 6, 1 upon 10 raised to the power minus 6, that means 0.0000000 and 6, right? So basically we will neglect it because it is very, very low. So what happens here? 1 upon r positive. That means hydration enthalpy inversely proportional to the radius of cation. If cation is smaller, hydration enthalpy will be larger. Are you getting my point?
Yes.
Now come to the lattice enthalpy. Lattice enthalpy has a formula that is also here. It will be kq1 q2. That won't matter here. 1 upon r plus plus r minus. Now you know that r minus is already very larger since we are taking larger anions. So cation will be very, very small in front of the size of anions. So we will neglect it because a value which has anything which is very low value and we are going to add in a big value, that low value has no effect on the bigger value. Are you getting my point?
Yes.
So here it will be r minus. That means lattice enthalpy inversely proportional to the inversely proportional to the radius of an ion, and radius of an ion here is very basically same. Radius of an ion is same. Now we know that where there is hydration enthalpy high, the solubility will be high. Is that clear?
Yes.
That's why it comes in this order. Just write it.
Done.
Wait a minute. So if I'm going to give you a question, LiNO3, NaNO3, KNO3, RbNO3, CsNO3. Just write the order of solubility. Can you do this?
Yes.
Very good.
LiNO3 will have high solubility.
Yes. Down the group decreases.
Yes.
Very good. Just write it. Now, another important point I'm going to write regarding solubility is that generally this is basically conclusion, or you can say notes. Generally, anions are larger in size. So, solubility decreases from top to bottom, right?
Yes.
But here is the important point. But in case of 1A, that means first group. If anion is F minus O minus 2, CO3 minus 2. In case of first group, I'm talking about HSO4 minus, SO4 minus 2, and SO3 minus 2. And in case of 2A, that means second group. That means we are talking about second group, and the anion is F minus, O minus 2, and OH minus. Solubility increases from top to bottom. Solubility increases from top to bottom. So I'm going to give you a question on this base. BeCO3, MgCO3, CaCO3, SrCO3, BaCO3. And another question, Li2CO3, Na2CO3, K2CO3, Rb2CO3, CS2CO3. EO, MgO, CaO, SRO, BeO. Can you arrange this all? Order of solubility.
For first one, beryllium has highest solubility. Barium has lowest. For
Very,
second one, lithium has lowest.
very good.
For third one, beryllium has lowest.
Very good. So can we change the slide? Yes.
1 second. Done.
Okay, moving to the next. Beryllium oxide is almost insoluble in water and barium we are talking about just don't talk about beryllium oxide. BeSO4 beryllium and and beryllium sulfate is soluble in water. Why? Why it is so? Because you know that BeO, it has more lattice enthalpy. It has more lattice enthalpy. If enthalpy is high, lattice enthalpy is high, it will be less soluble. So I'm going to write it's why it's more enthalpy, lattice enthalpy, because a smaller size of cation. Because of a smaller size cation form a stronger bond. Form a stronger bond with a smaller anion. With a smaller anion. Now we are going to talk about BeSO4. It has less lattice enthalpy and more hydration enthalpy due to large difference in the size of cation and anion. जहां भी लैटिस एंथैल्पी डिक्रीज कर जाता है वहां सॉल्युबिलिटी इंक्रीज कर जाता है.
Done.
Done.
Yes.
Now we will talk about thermal stability. Thermal stability. So basically thermal stability is so easy to understand here because I have already taught you about polarization and Fajan's rule, right?
Yes.
Since we are talking about first group, it will make ionic compound most probably. So if there is monoatomic anion, you can easily recognize it where which is monoatomic and which is polyatomic, right?
Yes.
So here is the thing, monoatomic anion, that means O minus 2, you can take it N minus 3, F minus, Cl minus, Br minus, I minus, it's all monoatomic anion. Now what happens whenever there is monoatomic anion, thermal stability will be compared with lattice energy. The more lattice energy, the more thermal stability. And you know that lattice and enthalpy is directly proportional to magnitude of charge, and inversely proportional to lattice enthalpy, inversely proportional to size of ions. Now polyatomic anion, whenever there is polyatomic anion like CO3 minus 2, and you can say that SO4 minus 2 as well as HCO3 minus, you can easily recognize it, right, etc. Then you have to check the polarization, and thermal stability is inversely proportional to polarization. Thermal stability inversely proportional to polarization. And you know that polarization power, PP, I'm talking about PP, polarization power is directly proportional to covalent character, which is inversely proportional to thermal stability. The compound which is more polar, or which have more polarization power, that compound will be more covalent and the thermal stability of that compound will be lesser. Is that clear?
Yes.
Just write it.
Done.
Okay. Order of thermal stability. Now we will talk about order of thermal stability. You have to arrange it. The question is basically BeCO3 and then MgCO3, then CaCO3, and then SrCO3, and then BaCO3. Can you solve it, or should I start explaining?
Yes.
What's your answer, Akifah? Whenever order of stability, thermal stability will be asked, what you have to do is just concentrate on anion. You can see that this is polyatomic anion and this is also polyatomic anion. First, polyatomic anion, that is we calculate it or arrange it in order of thermal stability inversely proportional to polarization. And you know that polarization that comes inversely proportional to size of cation. So here the polarization power is very high. That means covalent character is very high. That means thermal stability is very low. So the order will be like this. In the same way, the order will be like this for the second order, right?
Yes.
Okay, just write it and let me know.
Done.
Okay. Wait a minute. Okay. Carbonate. Oh, wait a minute. Okay. Just write a carbonate. Metal carbonate. So just write metal carbonate. So metal, how does metal react to form carbonate? You know that this is metal carbonate. If you will heat it, metal oxide and CO2 will be released. In the same way, calcium, CaCO3, metal oxide, that means, sorry, CaO, here CaO, calcium oxide plus CO2. Li2CO3, if you will heat it, Li2O plus CO2. Now, the problem is that only lithium from the first group element will dissociate or will decompose into lithium oxide and carbon dioxide. But the rest of the elements of carbonate from first group will not decompose into metal oxide and carbon dioxide. If you will give more and more heat, it will melt, but it won't decompose. So I'm going to write a conclusion. All carbonates decomposes, all carbon decomposes into metal oxide and carbon dioxide. upon heating. But, or you can say except sodium, potassium, rubidium, cesium. This. So if you are going to decompose sodium carbonate, it won't decompose, either it will melt. In spite of instead of decomposes, it melts, but it won't decompose. Just write it and let me know.
Done.
Very good. Now here we are going for metal bicarbonate. Metal bicarbonate. So here is metal bicarbonate. If we will heat it, if we will give heat to it, then it will form metal carbonate plus water H2O with CO2, carbon monoxide, carbon dioxide. Again, LiHCO3 here, bicarbonate or hydrogen carbonate. If you will heat it, it will be converted into Li2CO3 plus CO2 plus H2. In the same way, magnesium also do. If you will heat it, it will be converted into magnesium carbonate, then H2O, or then CO2. The question arises here is, arrange in increasing order of thermal stability. Can you arrange it?
Yes, 1 second. Lithium has less thermal stability.
Lowest thermal stability and maximum this, right?
Yes.
Now we will go for metal nitrate, NO3. This is metal nitrate. If you are going to heat it, then metal oxide plus nitrogen dioxide along with oxygen gas will be released. This is called brown gas. This is basically brown gas. Color of the gas is brown also. So if you are going to take LiNO3, so metal oxide, so it will be Li2O. So for balancing, I'm going to multiply it by 2, and then NO2, and then O2. Again, if you are going to take reaction from second group, it will be also like same, beryllium oxide, and then 2NO2, and then half O2. Simple, just like this. Okay.
Okay.
Just write it. Always remember MnO3, if heated, then if heated, this M here is sodium, potassium, rubidium, and cesium. It will be converted into metal nitrate, MnO2. It will be converted into metal nitrate. This is metal nitrite. MnO3 is nitrate, NO2 is nitrite along with N2 plus O2. But if you will continuously heat it, then it will be converted into metal oxide and then N2 plus O2. Okay. Strongly, if you are giving a strong heat, then it will be like this. Just write it and let me know.
Done.
So basically, if you are going to write sodium nitrate and if you are going to heat it, first the reaction will be NaNO2. The first reaction will be NaNO2 and half O2 like this. And the temperature should be greater than 400 degrees centigrade. Okay, then only it is possible. Done.
Done.
Okay, can I change the slide?
Yes.
Wait a minute. No. Write a topic: anomalous behavior of lithium. Why does lithium shows anomalous behavior?
Done.
Due to, very good, extremely smaller size of, due to extremely smaller size of lithium and lithium plus. Second point we can write, due to very high, since Li plus has very smaller size, that means very high polarizing power of Li plus because it is very small, and also due to very high ionization energy. Why it's it's high ionization energy? Because it's very small. Right?
Yes.
We have some important points regarding lithium and magnesium. Basically they show diagonal relationship, the relationship which are the properties which are similar to lithium and magnesium. That's why they are known as this relation is known as diagonal relationship. It is basically like diagonal. Lithium is here, beryllium, sodium is here, and here magnesium is present, and you know this has some similar properties like magnesium. That's why it is called diagonal relationship. I'm going to show this. Lithium and magnesium shows diagonal relationship, the first one. Again, in the next point, lithium and magnesium are harder in their group. They are harder. Again, lithium and magnesium reacts with cold water. Reacts with cold water. Lithium and magnesium done. Now see, Li2CO3 and MgCO3 decomposes on heating to give metal oxide and carbon dioxide. Next point, LiCl and MgCl2 are deliquescent. That means they absorb moisture. Deliquescent, that means absorbs moisture. Since the hydration enthalpy of LiCl is very high, so it exists as LiCl.2H2O, and MgCl2 is also like MgCl2.8H2. So these all are similarity between lithium and magnesium. Just write it and let me know if you are done with this. And according to deleted syllabus, it is done in this chapter.
Done.
So we are going to start P block. Done.
Yes.
Very good. Very good. P block is quite a small chapter. P block. So basically, we are going to study about group 13 elements, boron family. And boron family has 5 elements: boron, aluminum, gallium, indium, and thallium. Now see how we find atomic number in group. There is a magic number. We know the atomic number of we know the atomic number of boron 5. Whenever you want to calculate the atomic number of next atom and next element in the same group, you just add 8. So it will be basically 13. Again, when you are going moving next, then again add 18. 5 plus 8, that will be 13. 13 plus 18, that will be 31. Again you have to add 18, so it will be 49, and then you will add 32 at last, it will be 81. In P block element, if second group element, if you know the atomic number of the second group element, second period element, you can easily find the atomic number of all the elements in that group. In P block, you have to add 8, 18, 18, 32. Is that clear?
Yes.
Now I'm going to write the electronic configuration. So it will be 2s2 2p1. Here it will be neon, and then 3s2 3p1. And here it will be gallium, that means argon. 3d10 4s2 4p1. Again indium, after argon it comes krypton, or and it will be 4d10 5s2 5p1. And after thallium it will be xenon, it will be 4f14, and then 5d10, and then 6s2 and 6p1. It's atomic number electronic configuration of group 13 elements.
Done.
Very good. Now starting its properties. Right. Oxidation state. Write a topic. Oxidation state. See, what is the oxidation state? Group 13 elements shows 2 type of oxidation state. Due to its valence electron 3, or you can say ns2np1 configuration, it shows +3 oxidation state. And due to 4f, this f and d, poor shielding effect of this f and d, d and f subshell, it shows +1 oxidation state also. So I'm going to write group 13, write with me. Group 13 element. So +3 oxidation state due to NS2 NP1 configuration. Next point you can write group 13 elements show +1 oxidation state due to inert pair effect. Due to inert pair effect. Due to inert pair effect, it can easily donate 1 electron. That's why it also shows +1 oxidation state. So basically, in this group, on top, the elements on the top will show the elements on the top will show higher oxidation state. They will be stable in higher oxidation state, and in the in the bottom elements will show lower oxidation state. That means they will be more stable in lower oxidation state than higher oxidation state. This is the order of stability. And remember one thing, thallium in +3 oxidation state is highly unstable. Highly unstable. So there is a question, calculate oxidation state of thallium in TlCl3. Can you calculate it, Akifah?
No, can you explain? Can you explain?
Yeah. You know, if you are going to calculate the oxidation state according to, have you written it all above it above this question?
Yes.
Okay. Now see, if you are going to calculate it, the oxidation state of thallium, just take it as X plus. How many chlorines are here? 3, and one chlorine. The oxidation state of one chlorine is -1 generally, so it will be like this, and X is equal to +3. So oxidation state of thallium will be
Plus.
+3, but this is wrong because I told you that thallium in +3 oxidation state is highly unstable, right?
Yes.
So basically highly unstable. So here the oxidation state of thallium is Tl plus. How it is possible? Basically, you know how these compounds form. Thallium exists in plus, and this Cl3, just take it I3. That will be more convenient. I3, and this I3 will exist in I3 minus, and here only a force of attraction ionic bond is formed, right?
Yes.
So that's why it exists in +1 oxidation state, because in +3 oxidation state it is very highly unstable. Okay, so it just try to remember it. Okay.
Okay.
Now write with me order of stability of +1 oxidation state. What will be the order? Order is so easy. Down, the elements which present in the bottom will be more stable in +1 oxidation state as compared to the upper top elements. Just write it. What is the reason? Due to poor shielding effect. This Se represents poor shielding effect of D and F subshell. D and F subshell. Force of attraction from the nucleus increases on valence as subshell. Okay.
Done.
Very good. Now we will start like oxidation state we just did. First, we are going to discuss about atomic size. See, the atomic size is basically we are talking about boron, aluminum, gallium, indium, and thallium. This is understood. 13th group. Okay. So if you want to arrange in atomic size, uh, the larger size will be of thallium and then indium, or you can arrange it like this: boron, and then what will come? Can you arrange it? Akifah, can you arrange it?
Aluminum.
Aluminium, right? No, it will be gallium, then aluminum, then indium, then thallium. Okay, why this is so? Because of this poor shielding effect. Because of its poor shielding effect, or you can see due to poor shielding effect, its Z effective increases. That's why the size of gallium decreases, even it is smaller than aluminum. So just keep it in mind, very important. Okay. Okay, come to the ionization energy part. See, ionization energy has a order: boron, then thallium. Down the group, ionization energy decreases. Basically, this 13th group element is called heterogeneous group, because it just comes after D block, and D block had very variation, very much variation. So boron, thallium, and then gallium, and then aluminum, and then indium. Why does it so? Because here Z effective increases, and due to Z effective increases, nuclear charge increases due to poor shielding effect. Poor shielding effect of F subshell, 4F subshell. Nuclear charge increases, force of attraction increases. So if you want to remove electron, the force of the force of attraction is so high, you have to give more and more energy, even more than gallium, aluminum, and iodine. And the fourth is melting point. And the fourth is melting point. Generally, non-metal are non-metal has lesser melting point. Just write it and let me know.
Done.
Wait a minute. Okay, so now we will talk about melting point. You know, beryllium, aluminum, gallium, and then indium, and then thallium. This is non-metal, and after that, all are metal. Generally, metal has more boiling and melting point than non-metal. But what happens here is boron has more melting point than aluminum, then indium, then thallium, then gallium. Gallium has lowest melting point. It even melt at 30 degrees centigrade. If you keep it on your palm, it will melt. Why does it so? Basically, this non-metal boron actually exists in icosahedral structure. That means a crystalline solid. The molecules in icosahedral structure is so tightly packed that they have very more force of attraction between their particles. That's why it has very large melting point than other metals. So I'm going to write generally metal has higher melting point than non-metal, but boron has higher melting point due to icosahedral structure, hard crystalline solid. So order of melting point is this.
Done.
All done.
Yes.
Okay. So write about gallium. Gallium has usually low melting point because gallium melts when it is kept on palm. So melting point of gallium is 30 degrees centigrade and body temperature is 32 degrees centigrade. Gallium is liquid in summer and becomes solid in winter.
Done.
Very good. Now that's very important. We are going to do it for boiling point. Can you arrange it in boiling point? See what is the difference. Boiling point, boron, then aluminum. This is the same. This will be the downward. It will be decreases. Since boiling point, this has icosahedral structure. That's why it has more, and all are here metallic bond, a strong metallic bond. If size increases, metallic bond strength of metallic bond decreases. So it all has a strong metallic bond. That's why in downward boiling point decreases. Just write it.
Done.
Now write a topic, chemical properties. we will talk about nature of compound. Since you know that boron is very small in size and it has 3 electrons, so it's very tough to remove all the 3 electrons to form ionic compound. That's why boron, to form B plus 3, the ionization energy is very high. The ionization energy is very high. So it will form covalent compound. Covalent compound. Okay,
Okay.
just write it. As the size increases down the group, ionization energy decreases because the size increases. So ionic character increases. So I can write, as the size of atom increases, ionization energy decreases. So ionic character increases. So with this reference, I'm going to write LCl3 in solid state. In solid, it is covalent. LCl3 in H2O is ionic. GaCl3 in solid is covalent, and GaCl3 in H2O is ionic. And here InCl3 or TLO, always ionic. Just write it and let me know.
Done.
All done?
Yes.
Very good. Write a topic, a reaction with air. Air, that means O2 plus N2. See here, boron has two forms. Boron has two forms. One is crystalline and another is amorphous. And crystalline form of boron does not react with water, so I'm going to write crystalline form of boron does not react with air, but amorphous form of boron react with air to form B2O3, that is boric anhydride. Okay, just write it.
What does amorphous mean?
Amorphous, basically, there are two types of solid on the basis of arrangement of particles. Here you can see crystalline solid are those solid which are orderly arranged for long range, and amorphous solids are those which are arranged in short order. For example, crystalline solids are like iron, you can say NaCl, ZnS, and amorphous solid is like glass, rubber, plastic. It's all amorphous. Okay.
Okay,
Okay, just write it.
done.
So if you are going to react with oxygen, it will be B2O3. Just write with me. If you are going to react aluminum with oxygen, it will be Al2O3, and Ga plus O2, that will be Ga2O3. Indium, that will be In2O3, and then thallium, that will be Tl2O. So this is basically acidic in nature because non-metallic oxide is acidic in nature. Al2O3 and these are amphoteric in nature. These are amphoteric in nature, and these are basic in nature. Since they are metals, so metallic oxide, basic in nature. Just write it.
Done.
Very good. अब देखिए यहाँ पे चूंकि ऑक्सीजन से कर दिए हम लोग, और हम क्या कर रहे थे, और नाइट्रोजन की बात कर रहे थे, एयर की बात कर रहे थे, तो उसमें तो नाइट्रोजन भी होता है. सो बोरोन नाइट्रोजन से रिएक्ट करेगा तो यहाँ बनाता है Bn, जिसे हम क्या कहते हैं, बोरोन नाइट्राइट. अगर एल्युमिनियम से रिएक्ट करेगा तो हम बोलेंगे Aln, एल्यूमिनियम नाइट्राइट. Gallium, indium, and thallium does not react with nitrogen. And one thing remember, Bn to the whole x is basically inorganic benzene. This is inorganic benzene.
Done.
Sorry, don't write inorganic, it's inorganic graphite. Just write it down. Inorganic benzene. Done.
Done.
Now see, conclusion, or you can say note. If you are going to react boron with air, there will be two products. The first one is B2O3 and the second one is Bn. If you are going to react aluminum with air, the first product, there will be two product, Al2O3 as aluminum and aluminum nitride. If you are going to react with gallium, indium, thallium with air, only oxide will be formed, but no nitride. Is this clear?
Yes.
Just write it.
Done.
Okay. Write a topic. The reaction with acid and alkalis. First, we are going to take amphoteric metal. I will give a list of amphoteric metal and write a point. The metal which liberates hydrogen or H2 gas with acid or with a strong acid and a strong base is called amphoteric metal. As for example, beryllium, aluminum, zinc, tin, lead. These all are amphoteric metal. Just write it and we will continue from here in the coming Tuesday.
Done.
Okay. So Akifah, we will start from here in the next class. Okay.
Okay.